Unit 4, Day 2, Part 2. So what I did, I wrote in, you switch videos, is I typed this in the calculator and found out that my lowest cutoff value right here is about 541. And my Q3 cutoff value is about 558, right there. And so for Q3 minus Q1, we have an IQR of 16.2, which makes sense because if you think about it, okay, if you think about it, the middle from here to here has about 68% of the data. The IQR has 50%. Well, the standard deviation is 12. So 12 plus 12 is 24. Okay, so there should be 24 different values in here, and we want a little less than that, and we got 16.2. So that makes sense. That means that 50% of the bags have a range of having M&Ms between 542 and 558. So there's a value in there about 16. Okay. Next question. If the company wants to guarantee that no more than 5% of the bags have fewer than 540 M&Ms, what mean should they try to achieve so they can adjust their machines? Okay, so we want the bags to have fewer than 5%, or we want fewer than 5% to have 540 or less, but we don't know what the mean is. Well, what we have to do is find the standard deviation, is to find the z-score for 5%. So what I can do is do inverse norm, and I put in 0.05, and at that point you actually could hit enter, but that will give you the cutoff score if your mean is 0 and your standard deviation is 1. And if you do that, you will get a z-score of negative 1.64. This is the z-score for 5% below the mean. Okay, like this is the z-score for this value. So if we were to redo it, if this was 0, this would be negative 1.64. Okay, and then we put it into our z-score formula. So the point we know is 540 minus the average we want to find. Divide that by 12, equaling negative 1.64. Go ahead and times both sides by 12. Okay, and you would get 540 minus x bar, and that is negative 1.64 times 12. That gives you negative 19.68 minus 540 from both sides. Again, some of you can just see how to do this in your head. Thought I'd give you one example of the algebra. So we get a negative x bar and a negative 559.68, which means the mean that they would want is about 560. Okay, so it's approximately 560, although if you were to check it in the calculator, you would want to use 559.6. I'm having issues with my stylus, excuse me. 8. And what I mean by check is let's see if that's true. So let's go back on, clear this out, to our distribution, normal CDF, and we want to see if we're at 540, so from negative infinity up to 540, and if we had a mean of 559.68, okay, again, you could do 560, it'd just be off a little. With this, again, in the same standard deviation of 12, will that give us 5%? Hey, yes it does. So if they wanted less than 5% to have, or if they wanted 5% or less to have 540 or less, they'd need to change the mean of the machine to 560 instead of 550. We're going to do one more like that, okay? But in this case, the mean will stay 550, but we want a new standard deviation. So we already know the 5% z-score is negative 1.64. Okay, so we're still doing the same picture over here with the 5%, but we just do a different formula. So we say, well, we're looking at 540 minus the mean, oh my goodness gracious, minus the mean of 550 all over some standard deviation. We can do sigma or s there that we don't know. And that's got to equal negative 1.64. Okay, which gives you negative 10. Equaling negative 1.64. So we're going to times both sides by s. We get negative 10 equals negative 1.64s. Divide by negative 1.64, and you'll get an s that should be about 6.09. So they need to cut their standard deviation in half, okay, if they want to do that. So we could check ourselves again if we really wanted to, and I promise you that that would come out. All right, last little bit, assessing normality. In many problems, we assume the distribution is normal. In real life, however, a set of data will never be exactly normal. Still, the normal model can be useful if the data are close to normally distributed. To check to see if a data set is normally distributed, we could look at a dot plot, a histogram, or a stem plot, since both of these show symmetry, skewness, and modes. A box plot can also show symmetry and skewness, but not where the modes are. We need it to be unimodal. However, even dot plots, histograms, and stem plots are not as useful as an MPP or an NQP, which is a normal probability plot. In a normal probability plot, the actual data values are plotted on one axis, and each value's theoretical z-score is plotted on the other axis. For example, in a data set with 100 values from a normal distribution, the smallest value should have a z-score of negative 2.58. To estimate this value, imagine taking many samples of size 100 from a normal distribution and sorting them, and finding the average z-score for the minimum value in each sample. The average z-score of these minimums should be about 2.58. We can talk about that in class. If a data set closely follows a normal distribution, then the NPP should look linear. However, if the NPP is not linear, then this gives evidence that a normal model may not be appropriate. So just like with least square regression, where you put your data in and you check the residual plot to see if it was linear, here you'll put your data in. Okay, so in this case we have some data. It looks fairly normal. And then you pick a normal probability plot, and if it plots linear, then normal is a good fit for it. And we will do this in class and play with it. All right, do not do homework 7. That'll be assigned. Okay, so finish homework 6 and do your reading. Have a good night.